reintroduce you and let's just get going with your presentation that you see on the screen about the REM project in Montreal.
Jalal, thanks for the opportunity. So I'll be talking, I'm going to be talking about the design of drill shaft we adopted for the REM project in Montreal using axial and lateral static load test. I will start, by providing, a brief description of the project and then the objectives of the static load test. Then I'll be talking about the result and analysis of the axial load test we performed in limestone, dolomite, and shale. And then the result and analysis of the lateral load test we did, in cohesive soil and cohesionless soil. Then I talk briefly, about the cost saving by doing, axial load test, and I will end with some concluding remarks. So what's the REM project? REM stands for Réseau Express Métropolitain in French, rough translation, light rail transit. It's a $6.3 billion design-build project that's been constructed and designed by a joint venture called Lavelin. The design team is led by SNC Lavelin, my company, and AECOM. The total length of the project of the network is about 42 miles, out of which about 15 miles is on elevated structures. The tunnel is 2 miles and total number of stations 26. So we have, on the project, 650 drill shafts to be constructed. The project consists of 4 segments. Here is, the Montreal Island. Here you can see. The first segment, is the South Shore segment on the South Shore of Montreal. It starts, at the commercial district, on the South Shore of Montreal called Dixtrans, and it goes all the way to downtown Montreal. Out in this segment here, we have about, 2 miles of elevated structure in this area here. Then we have, the DM segment here, the Montagne segment. It goes to this town here, the Montagne. It's mostly at grade, even though, we have, a 50-span structure in this area here. The SADB segment, it goes to Saint-Anne-de-Bellevue. This is all elevated. It's 17 kilometers of elevated structure. It's a 340-span structure. Then, the last segment, is the airport segment. We have, about, 2 miles of elevated structure. It goes to the Trudeau International Airport. The rock formation, along the project, we have shale on the South Shore side of Montreal, and in Montreal Island, it's basically limestone and dolomite. Design criteria for the project: design life, is 100 years. The seismic design, was performed, for 2% in 50 years. Peak ground acceleration 0.38 G, and the magnitude 6.4. Those are typical values for the Montreal area. The standard we used for the project, first, the Canadian Highway Bridge Design Code. In terms of foundation engineering, we use, the Canadian Foundation Engineering Manual, and then AASHTO Bridge Design Specification. Foundation type, we use, a drill shaft for all substructures socketed into rock. Diameter of the shaft varied between 6 to 12 feet. And the socket length into sound rock varied between 1 diameter and 2 diameters, so roughly between 12 feet and 24 feet. Here are some pictures during construction. As you can see, each substructure consists of a single column supported by a single drill shaft. And once constructed, it's going to look like that. Here's, the structure I was talking about, the SADB segment, the 340-span structure. It runs parallel to Highway 40 in Montreal. And here's the bridge crossing over the St. Lawrence River between Nuns Island and Montreal. The train will, on the South Shore segment, the train goes over the brand new Champlain Bridge. This bridge, was open to traffic only a few months ago, and it was also designed and constructed by SNC Lavelin. So when we started, on the project, we had, 2 objectives in mind. First of all, to do a thorough analysis. Why we need to do a thorough analysis? Because each substructure is supported by a single drill shaft, so there is no room for mistake. Any mistake, let's say, could be catastrophic. And second, to optimize the design. So by mutual agreement between, let's say, the construction team and the design team, we decided to perform three axial load tests in each of the rock formation, one in limestone, one in dolomite, and one in shale. And also two lateral load tests at the DM segment and in SIDB segment, one in cohesionless soil, one in clayey soil, cohesive soil. Why do we do, let's say, axial load test? Is basically to optimize design. So we know, let's say, like the axial load, the axial capacity of a drill shaft, the unit side friction here. This equation here, let's say, is given in AASHTO or the Canadian manual. Let's say the unit side friction depends basically, I'm going to get into this equation later on, but it depends on this empirical parameter here, C, which is very variable. So by doing, let's say, an axial load test, we can calibrate, back calculate, let's say, this parameter here and have more accurate estimate of the skin friction. Also, we can determine more accurately, let's say, the tip resistance contribution. We know when we apply, let's say, an axial load on a drill shaft, the load is taken basically by the skin friction along the rock socket and the tip resistance. So how much, let's say, the tip resistance contribution, let's say, you know, some engineers just ignore the tip resistance to be conservative. Some other engineers, let's say, just limit, let's say, the tip resistance to 10% or 15%. By doing, let's say, an axial load test, we can have more accurate estimate, let's say, of tip resistance contribution. Also, we can develop, let's say, a load settlement curve for settlement analysis at the service limit state. And we can use a higher resistance factor, which means a lot of saving. As far as lateral load test, we do that, let's say, to validate and calibrate the PY curves to be used, let's say, in the analysis. For those who are not really familiar, let's say, with the axial load test, let's say, so how do we do that? Let's say, first, we construct, let's say, a sacrificial drill shaft using exactly, let's say, the same mean and tool as for production shaft. We install an O-cell, Osterberg cell, in the bottom of the shaft here. We increase, let's say, the pressure in the O-cell until failure. The bottom plate here will move downward, will provide information about the tip resistance. The upper plate will move upward, and along with the strain gauges installed inside the shaft, will provide information about the skin friction. So here's, let's say, the results of the axial load test, let's say, we did in dolomite and limestone. As you can see, let's say, at the end of the test, the maximum load was 40.7 meganewton or 9,000 pips, 20.5 going downward, 20.2 going upward. The upward displacement at the end of the test varied between 2.1 millimeter, 3.6 millimeter, and the downward displacement, the red line here, varied between about 10 millimeter and 14 millimeter. We plotted here the unit skin friction versus displacement for dolomite and limestone, and we see, let's say, like the total mobilized unit skin friction at the end of the test was equal to 1.8 megapascal, let's say, in dolomite, about 37.5 KSF, and 1.9 megapascal, let's say, in limestone, about 39 KSF. In case of shale, the maximum mobilized unit skin friction was equal to 1.6 megapascal. So going back, let's say, to this equation, as I was talking about, let's say, earlier, knowing the unit skin friction, F sub S here, Q sub U is the unconfined compressive strength of the rock, and PA is the atmospheric pressure. So we plug this number, let's say, into this equation, and this parameter, this empirical parameter here, C, can be back calculated, and we found that C was equal to 0.82 in dolomite, 0.92 in limestone, and 1 in shale. Now, the question was, how do we calibrate? Let's say we had only 3 load tests along the project, and how do we use the result of this only 3 load tests for the design of 650 shaft? I'm not going to go into details in that, but to do that, let's say we introduce, let's say, this parameter alpha here. Let's say you can see here alpha. It's called, let's say, the joint modification factor. is given, let's say, in AASHTO by this table here. It depends on the rock quality, basically, on the RQD along the socket and the joint condition. So whether the joints are open or closed. So we introduce, let's say, this parameter into the equation here. And the bottom line, the skin friction was scaled up or down, depending, let's say, on the rock quality at a specific location to the rock quality at the load test location. As far as the tip resistance, as I mentioned earlier, let's say the question is how much, let's say, the tip resistance contribution, let's say how much of the total load that's transferred to the tip. We know it's well documented in the literature, the tip and the skin friction do not mobilize, let's say, at the same displacement. The skin friction is generally fully mobilized, let's say, at a displacement of about 0.5 inch or 13 millimeter. The tip is fully mobilized, let's say, at much larger displacement, usually it's depending, let's say, on the shaft diameter. So anyway, let's say we calculated, let's say, the ultimate tip resistance at the load test location using, let's say, the equation here, let's say, that's given, let's say, in the Canadian Engineering Manual, or the equation that's given, let's say, in AASHTO here, this equation here that depends, let's say, on the Hawke-Brown parameters. Either equation, let's say, give approximately, let's say, the same result. We had, let's say, the ultimate tip resistance of varying between 60 megapascal and 175 megapascal. For the load test, let's say at the load test, at the end of the test, the mobilized unit skin friction in dolomite, sorry, not the skin friction, the mobilized, let's say, end bearing in dolomite and limestone was only 19 megapascal, and in shale was 16 megapascal, so much lower than the ultimate tip resistance. So we can conclude, let's say, at a displacement in the range between 10 to 14 millimeter, only fraction of the ultimate end bearing was mobilized when the skin friction was fully mobilized. Can you go to the next slide, please? So here, let's say, we plotted the skin friction and the tip resistance on the same graph against, let's say, the displacement. And we can see, let's say, when the skin friction here is fully mobilized, the tip contribution, tip resistance contribution in case of dolomite, let's say, was 30%, and in case of limestone was 19%. Next one, please. In case of shale, the percentage contribution, let's say, of the tip resistance was 23%. Next, please. So what do we do, let's say, when we don't have, let's say, a load test? Let's say, how can we estimate, let's say, the tip resistance contribution when we don't have, let's say, load test results? The Canadian Foundation Engineering Manual recommends the use, let's say, of Pell's and Turner approach. That's basically based, let's say, on the elastic solution. According to this approach here, the tip resistance contribution depends on the socket length, the socket diameter, and the ratio of the elastic modulus of concrete over the elastic modulus of the rock mass. The FHWA publication, let's say, drill shaft publication, recommend the use, let's say, of Carter and Callaway approach, which is almost similar, let's say, based also, let's say, on the elastic approach. So next one, please. So here's, let's say, a table showing, let's say, a comparison of the tip resistance contribution between the elastic theory and the load test results. As you can see here, let's say, for example, for limestone, if you take, let's say, the example of limestone, the elastic theory predicts the tip contribution between 8 and 12%, depending whether we use, let's say, the Pell's and Turner approach or the Carter and Callaway approach. The load test results showed us, let's say, it was about 19%. The same for dolomite, the elastic solution, let's say, it was between 18 and 14%. The load test result showed us it was about 30%. The same in shale, between 6 and 9, and we had, let's say, 23%. So we can see here, let's say, there is a lot of optimization to be done. The next, please. So as for the skin friction here, we had to find a way to calibrate, let's say, the load test result with regard, let's say, to the tip resistance to other locations, because only we have, let's say, 3 load tests, and we had to calibrate, let's say, this result to 650 shafts, where the rock, let's say, could be of different quality, the socket diameter could be different, and the socket lengths could be also different. Again, so I'm not going to go into details in this, but we adopted, let's say, the same approach we use, let's say, for the skin friction by introducing, let's say, an adjustment factor in order to do, let's say, this calibration. Next, please. As far as the resistance factor, here, let's say, you can see here, let's say, the table, let's say, that's given, let's say, in the Canadian bridge design code for the resistance factor. And you can see here, let's say, when we have, let's say, a static load test, the resistance factor to be used, we're allowed to use is 0.6 for a typical degree of understanding. If we don't have, let's say, a static load test and the analysis is only based on static analysis, the resistance factor is 0.4. So we see here that only by using, let's say, a different resistance factor, there is at least, let's say, 15% of cost saving. AASHTO allows us the use of 0.7 as a resistance factor when we have, let's say, a static load test, and 0.55 when the analysis is based on static analysis. Next, please. I'm going to talk briefly, let's say, about the lateral load test we performed on the project, two of them, one in cohesionless soil and one in cohesive soil. So here's, let's say, a figure, let's say, showing, let's say, the setup of the load test. First, we constructed, let's say, two drill shafts, identical drill shafts, about 20 feet apart. The first one was for the axial load, and that's, let's say, what I was talking about. And once the axial load test, let's say, was done, this shaft, let's say, served as a reaction pile for the lateral load test. The lateral for this shaft here, let's say, for lateral load test, we installed, let's say, an inclinometer inside, let's say, the shaft in order to get, let's say, the deflection along the depths of the shaft. We used also, let's say, OCell to apply the load. Next, please. For at the DM segment where cohesionless soil, let's say, was encountered, the stratigraphy, let's say, consisted basically, let's say, of 3 meters of granular fill over 3 meters of glacial till over 3 meters of fractured rock over sound rock. We simulated, let's say, the lateral load test, let's say, with L-pile, and we use, let's say, a different soil model for the PY curve. We use, let's say, the API sand model. We use, let's say, the Rees model, and the PY curve obtained from pressure meter test. Next, please. We plotted here the deflection versus depth at different load increments. And as you can see, let's say, the dashed line here, let's say, is load test result. And we see, let's say, the match is almost perfect, whether we use, let's say, the API sand model, the Rees, or the pressure meter test result. Next, please. Most importantly, let's say, we plotted, let's say, the lateral pile head deflection against, let's say, the applied load. Again, let's say, the dashed line here, let's say, is lateral load test result. And we see, let's say, here, let's say, the green line here, let's say, is the pressure, the result, let's say, from the pressure meter test, the PY curve obtained from pressure meter test. And we can see, let's say, like up to a displacement, up to a deflection, let's say, about 1 inch, 25 millimeter. The match was almost perfect. Let's say, at larger deflection, let's say, the pressure meter test, let's say, tends to overestimate the deflection. For larger displacement, we see, let's say, like the API sand model and the Rees model, let's say, match more accurately with the lateral load test results. Next, please. At the SADB segment where cohesive soil, let's say, was encountered, the stratigraphy consisted of 4.5 meters of clayey soil over 5.3 meters of glacial till. What happened, let's say, during construction of this one is that, let's say, before, let's say, the casing installation, the contractor, let's say, carried out a pre-hole in the clayey soil to facilitate, let's say, the placement of the casing. And also, during excavation of the soil inside the casing, the water level, let's say, was not maintained at the same level as the groundwater table. Result of that, let's say, was soil remolding, and that's obviously due to hydraulic gradient and running sand phenomenon. So we sent the investigation team again to the site to do some additional investigation as close as possible from the shaft. We did the SPT borings, vein shear test, and the cone penetration test. Next, please. The result of the investigation, let's say, confirmed that there was some soil remolding. As you can see here, let's say, we had, let's say, a 3 meter of silty clay soil. The undrained shear strength was 50 kPa before construction. After construction of the shaft, after soil remolding, this number dropped to 8.5 kPa. The same, the upper layer, let's say, of the silty clay, let's say, before construction, it was 70 kPa, the undrained shear strength. It dropped to 24. Even in the till layer, we had a 3.3 meter of glacial till. We estimated the friction angle to be 33 degrees. Before construction, it dropped to 28 degrees. Next, please. So again, we use, let's say, also, let's say, L5 to simulate, let's say, the lateral load test. In this case, we use, let's say, the API soft clay model with the disturbed soil parameter, this green line here, and the dashed line is the lateral load test result, and we see, let's say, the mesh was almost perfect. Only for comparison purposes, only, let's say, we used we simulated that, let's say, with the undisturbed soil parameter using, let's say, the same model, the API soft clay model, and we see, let's say, the response, let's say, was much stiffer. Next, please. Let's talk, let's say, briefly, let's say, about the cost saving. On the project, basically, let's say, typically, let's say, the factored axial structural load on each drill shaft, let's say, was about, let's say, 18 meganewton or 4,000 kips. The rock along the socket, let's say, was of good quality, about 70%. RQD, GSI, let's say, was about 60%. The shaft diameter varied between, as I mentioned earlier, between about 6.5 feet and 10 feet. Occasionally, we use a shaft, let's say, of 3 feet and 5 feet diameter. So let's take, let's say, the example, let's say, of 10 feet diameter shaft. If we don't have, let's say, any load test result, and we base all our analysis on the literature and the elastic solution, we would need, let's say, 15 feet, let's say, to support, let's say, the 4,000 kips. Now, let's say, using, let's say, the load test result, we need only, let's say, 5 feet. So this number, let's say, it's reduced, let's say, from 15 feet to 5 feet of rock socket. Okay, so we save, let's say, 10 feet of rock socket. Knowing that the typical cost of constructing a shaft in rock for a 10 feet diameter is about $6,000 per linear foot. That includes obviously drilling, let's say, into rock, concrete, rebar. So the saving, let's say, in this case is $60,000 per shaft for this, in this case, which is not negligible at all. Next one, please. The average saving, let's say, per shaft was $45,000 per shaft. We had a total number of 650 shafts. So the total saving, let's say, was $29 million. The load test cost was about $300,000. That included the construction of 3 sacrificial shafts and the load test cost itself. So we had, let's say, a total saving, let's say, on the project of $29 million. Next, please. So as a conclusion, we did, let's say, axial load test in limestone, dolomite, and shale, each of the rock formations, let's say, encountered on the project. The parameter, the empirical parameter C, let's say, was back calculated and was found to vary between 0.82 in limestone and 1 in shale. The tip resistance contribution, let's say, was found to be larger than what's predicted by the elastic solution, and we could use, let's say, a higher resistance factor. In terms of lateral load test, the back analysis in cohesionless soil and cohesive soil shows that only a slight adjustment needs to be done for the API sand model and the Reese criteria model, and that the pressure meter test is very powerful tool to predict lateral soil response. finally, the net saving for the project was $29 million. Thank you.
Riad, thank you very much for this very interesting presentation. That really drives home the point that when you do a little bit more testing, you definitely save money. In this case, 10-to-1 return.